What's up, guys? This is Jahangir from Edporium, and today we're going to be going into some more conceptual topics in chemistry. More specifically, let's talk about the forces and also the energy in bonds. So let's talk about the forces that are responsible in attraction and repulsion of these atoms, as well as energy, potential energy, and all that good stuff. So what we need to talk about first is all the forces that are a part of these covalent bonds. So the first one is going to be electron-electron repulsion. So electron and electron repulsion is this idea where if we looked at something like water, for example, so we're going to have H2O over here, and this is our loose structure. The electron-electron repulsion is when these two electrons are basically going to repulse each other, or they're basically going to sort of move away from each other. So if you think about our magnets example, and if you ever tried to sort of create an attraction with a north pole and north pole side of a magnet, or the both blue sides, it never works because they both repulse. But with electron-electron repulsion, it's when these two electrons repulse against each other. They pretty much want to move as far away from each other as possible, and this is actually what creates that bent structure. If we look at our Vesper diagrams, this in our water creates this sort of structure, this bend over here between those two hydrogens, and that's due to electron-electron repulsion. So the next one is going to be nucleus repulsion. So I'm just going to copy and paste this. So nucleus repulsion is very similar to electron repulsion, where if we brought our Bohr's diagram of an atom, let's just say this is its nucleus, and we're looking at hydrogen, for example. So hydrogen will have one valence electron, or one electron, and this is going to represent our nucleus. So in our nucleus, we're going to have one proton, one neutron. So we'll just represent it like that. And over here, same thing. Let's just say we had two hydrogens. So this nucleus repulsion is going to be between these two nuclei that sort of separates them out. So just like electron repulsion, this nucleus repulsion, when those nuclei come together, they're going to repulse. They're not going to attract each other. Now you might be wondering, well, what creates that attractive force that actually creates a covalent bond between, let's say, both hydrogens, creating this H2 or hydrogen gas? Well, that is going to be our nucleus electron attraction. And this is the nucleus electron attraction force that actually results in this covalent bond. Now here's the thing, this nucleus electron attraction must be equal to the electron repulsion and nucleus repulsion in order for our H2 to be in equilibrium or to hold a strong bond. Because if these repulsion forces are greater, then there won't be an attraction, and if this nucleus electron attraction is higher, then we're going to have a smaller atomic radius, making these two atoms very tightly and close together. Alright, so now let's look at this graph illustrating potential energy and internuclear distance. And for this example, we are going to be using H2, or our hydrogen gas. The H2 is gaseous form. So over here, we have a potential energy of negative 435 kilojoules per mole. And at this position, right over here, we're going to have our bond in which our nuclear and electron attraction forces will be equal to the total amount of repulsion forces, and this is actually where we find our sweet spot. This is where in our potential energy, this is the most stable bond, and this is the amount of potential energy we're going to have. Because you have to remember that if we have a lower potential energy, then we have a more stable bond. So more stable bond. So if we have less potential energy in our bonds, then our bonds are going to be more stable. Now if we increase our internuclear distance, so let's just say we sort of separate these hydrogens out, so we increase the distance between the two. When we have a longer distance, well, obviously we are going to have a higher potential energy, which means a less stable bond. And since we're separating them out, we're going to have a lower attractive force. And this makes sense because if we think about our magnets, there is a point in which those magnets will create an attractive force, and that's when they pretty much click. Now, if we move those magnets farther away, then we're going to decrease their attractive force, and it's going to be less likely for those magnets to basically click or bind to each other. So it's very similar with these bonds, and you can think of them as those magnets, where if we increase the distance between the two, then we're going to decrease the attractive force between them, and there's going to be more potential energy because we're increasing the distance. That results in a less stable bond. Now on the left hand side, we are decreasing in distance. So over here, we're having a shorter distance. Now, when we have a shorter distance, our repulsion forces will increase. So I'll just put increase in our forces, just to represent our repulsion forces, like the electron-electron and nucleus-nucleus. Now, the reason why is because when we decrease the distance, when we get those atoms, when we get those hydrogen atoms, when we push them closer together, the electron-to-electron repulsion forces will be higher, creating a higher potential energy. You can think about it as when we're bringing those atoms closer together, not only are the electrons getting closer together and they're going to repulse each other, the nuclei from those hydrogens will also repulse each other. So that creates an increased amount of repulsion forces, creating a lot of potential energy, and this results in an unstable bond. So we're going to increase in our repulsion forces, which results in an increase in potential energy. So over here, when we have an increase in potential energy, we're decreasing in attractive force, and over here, when we have a shorter distance, we're increasing in repulsion force, those repulsion forces. And that is why the bonds with the least potential energy are going to be the most stable bonds. Because this is where we hit our sweet spot in which our repulsion forces and our attractive forces will balance out, creating a very stable bond. And bringing it back to the magnet example, if we say both of these are the south pole, both of them will repulse. And if you try to move these magnets as close as possible as you can, they will try to move away from each other. They'll try to repulse to the point where when you try to move those magnets as close as you can, there's going to be a little bit of a force that you might feel, and the magnets will sort of break apart. They'll move away from each other. And this is exactly what's happening when we decrease that internuclear distance. When we move those magnets closer together, the repulsion forces will increase, and those atoms, those hydrogen atoms, want to move away from each other. So that is why when we decrease our internuclear distance, our repulsion forces will increase, and that results in an increase in potential energy. And over here, if we flipped our magnets around and we're moving somewhere like this is our north pole, this is our south pole. When we move these farther away from each other, increase that internuclear distance, we're going to have less of an attractive force, which increases our potential energy. So hopefully this video helped you understand what forces are contributing to these bonds forming. And the biggest thing you need to take out of this entire video is that if we have a lower potential energy, we have a more stable bond. So hopefully that helps, and as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.